So here I am again in the second video. Hopefully you can see me as I introduce the second video. I'm now going to stand behind the camera and we can have a look in detail at the level of these signals. So I mentioned these signals previously. We've got a yellow trace, which is the input signal to the amplifier, and the measured acceleration signal is the blue trace, the green trace being the velocity signal from the single beam instrument. We are asked to set the acceleration level to be to give an acceleration, a translational acceleration of 5 meters per second squared peak, and the sensitivity of the transducer is given over here on this box. So I have a sensitivity here of 94.96 millivolts per G, so nominally 100 millivolts per G. If I go over to my whiteboard here, I can convert from 94.96 millivolts per G to millivolts per meter per second squared, because we are working in meters per second squared. So dividing by 9.81 gives me 9.68 millivolts per meter per second squared. To get a 5 meters per second amplitude, acceleration amplitude, I therefore need to multiply this sensitivity by 5, which gives me 48.4 millivolts. And if we go back to the oscilloscope, you can see that my channel is being set up to have 50 millivolts per division, and these are the divisions on the oscilloscope: 1, 2, 3, 4. I have 8 divisions in total across here. Clearly it's a vibration, so this is plus minus 50 millivolts or 50 millivolts peak, and so one division at 50 millivolts per division gives me my acceleration level that I'm interested in. In terms of the laser vibrometer, I will adjust this to 2 output laser beams. I am going to focus those 2 beams on this angular wheel which is rotating. I have a circular cross section here and a square cross section alongside that. This is the measurement that I'm making of angular vibration, of just the rotation of the wheel. So now that I've changed the instrument to 2 beam output, I need to change the mode of the vibrometer to rotation from translation, and that will give me a different sensitivity in the right unit system. So I adjust to rotation, and then if I go back to the overview here on the panel, you can see I've got 6,000 degrees per second per volt, which is a huge dynamic range. I have nowhere near this amount of angular vibration, so I adjust this to 100 degrees per second per volt. It's a 10 volt output, so that gives me a maximum output of 1,000 degrees per second. Come back over to my oscilloscope. I've now adjusted the millivolts per division here because my signal coming from the vibrometer is increased. Previously we were at 50 millivolts per division, so we had lots of signals, you can see there. If we make the range of the oscilloscope larger, we have 500 millivolts per division, and within that, that signal level is 3 divisions, so that is a 1.5 volt output for angular velocity from the rotational vibrometer. You can see again that it's a little bit notchy, not particularly sinusoidal, and it corresponds to the acceleration signal from the accelerometer that's mounted to the rack. And of course with the wheel, because of the fact that as well as the backlash here in the gear system, we've got friction in the bearing. Of course we have an even less sinusoidal looking signal, but nevertheless in terms of the peak amplitude it's an acceptable measurement, and if we were to do a Fourier transform and look at the frequency content, we would clearly see that the primary sinusoidal vibration is at exactly the same frequency as which we're driving the instrument, of course. We can also, with this instrument, take measurements from square cross-section as well as an angular cross-section. So if I move the beams over onto the square section, you can see that there's essentially no sensitivity to cross-sectional shape variation. Exactly the same signal if I move them across from circular cross-section to square cross-section. The beam falls off a little bit, but once the beams are stable on the wheel, I get a good measurement of angular vibration. Now you have all of the